So for this example, I want to do a worked out example that's a bit more involved than what we saw in the previous video. So this is actually in exercise session 10. This is problem number 8. And we have to prove that n factorial is less than n plus 1 divided by 2 to the power n for n bigger than 1. So as before, if you have to prove something that depends on the parameter n, and n being a natural number, then oftentimes it's going to be a really good idea to look for mathematical induction. So let's do that here. And let's start with our starting case. So here you take your statement and you fill in sort of the smallest value for n that the problem statement allows. That's n is equal to 2 here because the statement starts at n is equal to 2. And so the right-hand side, the left-hand side rather, is 2 factorial. That's 2. And the right-hand side is 2 plus 1 divided by 2 to the power 2. So that's 3 halves squared. That's 9 over 4 or 2.25. And indeed, 2 is strictly smaller than 2.25. So we have our starting case. And now the induction step, that's the hard one. So here we assume that the property holds for a fixed value of n. So assume n factorial is less than n plus 1 divided by 2 to the power n. And now prove that n plus 1 factorial is less than n plus 2 divided by 2 to the power n plus 1. So here we just replaced all the n's by n plus 1. And so that warrants itself a small proof. So it's a proof within a proof. And we start from the left-hand side. So n plus 1 factorial. That's n plus 1 times n factorial. And now I can say that that's smaller than n plus 1 times n plus 1 over 2 to the power n. And why is that true? Well, that is precisely what I assume in my induction step. This is my hypothesis. And now let's clean it up a little bit. Let's bring all the n plus 1's together. So I get n plus 1 to the power n plus 1, and then divide it by 2 to the power n. And at this point in time, this is starting to look like the thing that we have to show. We have in particular that n plus 1 exponent here and here, so we're on the right track, but we're not there yet. We have an n plus 1, and the theorem wants an n plus 2. So how can we get that sorted out? I encourage you to pause the video and to try your hand, and I have to warn you, you have to use a couple of subtle tricks, but it's a fun problem to think about. So if you want to do it yourself, stop now, and then rejoin me when you're done. Okay, so I hope you had a chance to look at that and maybe even find the answer. So what we are going to do is we're going to step aside from the proof for a second, and we're going to relate what we have, n plus 1 to the power n plus 1, to what we want, n plus 2 to the power n plus 1. So we have this and we want that. And so now if you write it down like this, if you want to do something with an expression that involves an exponent, there's something that we have for that, and it's called the binomial theorem. So what we can do in particular is we can write n plus 2 to the power n plus 1, and write it as n plus 1 plus 1 to the power n plus 1. And that is a good thing, because now we can put this as my A in the binomial theorem and this as my B. And I can write this now as a sum k goes from 0 to n plus 1, the exponent, combinations n plus 1 k, and now n plus 1 to the power n plus 1 minus k. So the 1 to the power k, that's of course 1, so I'm not going to write that. Okay, that's starting to look very messy, but let's look at the first two terms of that expression. So let's write out the sum. N plus 1, 0. N plus 1, n plus 1 minus 0. And then the term for k is equal to 1. Okay, 1, n plus 1, n plus 1 minus 1. And then we have plus all the rest of the sum. So k is equal to 2, n plus 1, and then combinations. And I'm just not going to write them down because I'm not going to. And now let's clean up that expression. So what do I know? N plus 1 choose 0, that's always 1. N plus 1 choose 1, that's n plus 1. And then the last thing that I'm going to observe is that all of the terms that I have here, I don't know what they are, but they are all positive numbers. So they involve n's, which are positive, raising to a power, stays positive, and so on. So all of this here is positive. So what that gives me now is, if I remove these terms, so well, let me start with the other terms first. So if I write down what I have 1 times n plus 1 to the power n plus 1 plus n plus 1 here times n plus 1 to the power n, and then I have plus a bunch more positive things. So if I ignore that, then I end up with something that's strictly less. So what I have here is, instead of an equality, is I have a greater than sign. So I used to have a bunch of positive things that I've thrown away, and the price that I have to pay for is that these two terms are strictly less than these two terms plus the sign. And now that starts to get to look a bit nicer. So I have n plus 1 to the power n plus 1, and then n plus 1 times n plus 1 to the n plus 1, so that's also an exponent n plus 1, and I see that this becomes 2 times n plus 1 to the power n plus 1. And so what I get from this sub-proof here is that I can show that n plus 2 to the power n plus 1 is strictly bigger than 2 times n plus 1 to the power n plus 1. And that's a good thing to have, because now I can return to my original expression, and I can use that inequality because I have an n plus 1 to the power n plus 1. So I know that's less than n plus 2 to the power n plus 1 divided by 2 times, and I still have a 2. So I basically rewrote my sub-proof as n plus 1 to the power n plus 1 is less than n plus 2 to the power n plus 1 divided by 2. So that's the formula I'm using here. And now cleaning that up, I get n plus 2 to the power n plus 1, 2 to the power n plus 1, and I get n plus 2 divided by 2 to the power n plus 1. And that's precisely what I had to prove for my induction step. So that concludes my proof. I have my induction step, and now the starting and the induction step together, they combine to give me my full theorem. So you see, not an easy proof, because you have to often step aside and try on a piece of paper to see if you can massage the expressions in exactly the right way to make progress. But don't despair. If you get to a point where it doesn't make sense, write down what you have, write down what you want to have, and then see if there's a property that you can use that will make you turn one into the other. And in this case, here we use the binomial theorem.